Hello, everyone. This is Mr. Teo again. This is now week 7, and as you know, week 7 and week 8 there is a lab 5, and this lab 5 there is also a submission. Please take note that this lab 5 occupy week 7 and week 8. So I will be presenting to you how to do week 5 and a content, etc. But you only need to submit the week 5 submission on week 8, end of week 8. I will share with you the detail later when we talk about the slide. Yeah. So without further ado, let me share the slides with you for week lab 5. Okay. Let me turn off the floating panel, and then we shall start the slides. So as you know, lab 5 is about first and second order system. And also, please make sure that when you do your lab 5, the control and simulation add-on has already been installed for lab 5 to run. Same thing in your previous lab, lab 4, you already know that control and simulation add-on has to be on. Now, just a brief rundown on what is available here. There's many files, and you might look at it and get shocked. How come there's so many files? So first of all, there is one reference material, which is another previous lab. Basically, I included this lab because there is some steps inside this lab sheet that is required to insert some of the symbol in lab 5. So you basically may need to, if you start to modify the lab 5 VI that I gave you. There's a lab 5 VI which I put it inside the template. So if you do not modify, then I don't think you need to refer to this material. Then there is, of course, the lab sheet, lab 5 lab sheet, which is the lab sheet that we are going to use. So please go through the detailed steps, right? Now, lab 5 Zoom, later I will modify it into lab 5 slides, which is the slides for this, this presentation. And then, of course, finally, there will be an example of how the submission. As you can see, I need you to submit for all both N1, N2, N3 to submit exercise 3 and 4. And actually, there is actually total of 6 exercise. Exercise 1, 2, 3, 4, 5, 6. Now, exercise 1, 2, you need not submit. Exercise 3, 4, you submit. And exercise 5, 6 is the one that I'm going to give you some example on how to, what I expect of your submission. And now, again, this submission is pretty similar to lab 4 submission. Basically, you need to scan your results into a multi-page PDF and then name it as N1 or N2 or N3, whichever group you are in, and then the name followed by the name. And then, of course, when you submit your document, please click the link here and submit. Now, upload the VI. When you are done, please upload the VI for this exercise 4, right? 3 and 4. So basically for the exercise 4. And the deadline for submission is basically the last day of the week, which is 11th of June, 6 p.m. Now, anyone or more person, again, caught if, with a similar result of more than 80%, marks will be deducted. I will not inform you if I see it. So marks will be quietly deducted. So basically, also for the last one, submission later than the deadline, meaning that after this guy, marks will be prorated. So some people ask me, hey, if it is only prorated by 10%, 20%, it's okay, I can be late. But of course, if you go more than 2 days, the rate of proration become bigger, maybe like an additional of 20% proration. So therefore, please try to keep it within 1 or 2 days. So you still can get about 80, 90. Then after that, maybe you have is getting lower and lower. So this is to discourage people having the attitude of never mind lah, it's okay, we submit later. Because I know you are busy, we are also busy, so we need to keep track of the time and try to be timely with everything, right? Now, let's go on. So again, this is lab 5. Lab 5. So this is a lab for basically week 7 and week 8, and it's talking about introduction to first and second order system dynamic. Okay. Now, as I have mentioned, there is actually 6 exercises. The first exercise 1, 2 is for first order system with and without feedback, right? So this is on page 4 to page 6 of your lab sheet. And then of course, for lab exercise 3 and 4, which is your submission, this is for the second order system, and that is only on page 7, right? And likewise for exercise 5 and 6, it's also a second order system with and without feedback, and that is on the page 8. Later, I'm going to give you the example using exercise 5 and 6. So basically from exercise 5 and 6, you can infer how you should answer or submit the observation for your exercise 3 and 4, right? So basically we only do for N1, N2 and N3, you only do submission for exercise 3 and 4. Okay, now let's go through roughly what it means by a first order system. Now, a first order system, of course, in the time domain is the first derivative. It's the first derivative of y of t plus by t, and then of course with a k times by xt in the time domain. Now, if you take a Laplace transform into the frequency domain and rearrange the expression, you would get y of s over x of s, which is actually y of s is actually yt in the Laplace domain. X of s is actually xt in the Laplace domain. And this is what we call the gain function. Therefore, we write it as g of s, right? Which is x of s over y of s. And you will get k over tau s plus 1. This is in the s domain. Now, the reason why we call it a first order system is because we always, for any control system, we always look at the denominator. Now, this denominator, the highest power of s is actually 1. So therefore, we call it the first order, just looking at the power itself. Now, usually for a first order system, it will look something like that. Now, if I input a signal, which is a step function, that means from 0 all the way at time 0, I raise up the signal to 1 and then keep it flat again. This is a step function. Now, what happens when you do this to the system for a first order system? Now, the first order system will respond in this sense. So the output will be at time 0, it will start charging up. Start going up all the way until it hit the steady state value, which is very close to the steady state value. And this is the characteristic of a first order system. Now, of course, for the first order system with this kind of shape, there is a few ways that we like to characterize it. First of all, we want to look at the time constant tau. Now, time constant tau is the time taken from 0 to the point whereby the output reach about 63% of its final value. Now, we know that the final value, we are trying to hit 1, right? But of course, 63% will be about 0.63 volt. So this case, if you look down about 0.63 volt, 63% of the final value, you check the time taken, then this would be your time constant. That is one time constant. Now, and also we define the settling time, meaning that by the time it becomes a steady state, more or less reach a very constant value, steady states. And this is about 5 tau, 5 times of tau. So settling time will be 5 tau. And then of course, K is the steady states gain, whereby you cannot change anymore. It is the stabilized at that value, and that we call it K, right? So, okay, so the front panel that you are going to do for this exercise 3 and 4, 5 and 6, or 1 and 2 is going to be the same. So there is 3 of these front panel. In fact, I have given you the template, so you, in fact, no need to wire up the entire thing, and you just need to use the template, connect the connection. I didn't provide the connection, I just give you the symbol. So you don't change the symbol, you just do the connection and you run at the back panel, and you run, and basically you should be able to get it. So there is one observation of a waveform on the plant only, meaning that if I put an excitation into the plant, and depending on your expression for the plant, what should be the waveform? So this is a direct without feedback, right? Now, the one with a feedback will be the one that has a feedback connected, right? With the feedback connected. And this one, if you put in the same plant here, you key in the same plant transfer function. Of course, the controller, I am not playing with it for now, because we have not studied the controller yet. So therefore, we just put the controller as 1. That means 1 divided by 1, you get 1. So therefore, with that, you do a negative feedback, you would have a negative feedback transfer function that looks this way. So this is what we call a plant with feedback. So remember, exercise 1, we say plant with without feedback, and plant with feedback is referring to this graph and this graph, right? With and without feedback. Okay. Of course, there is another graph below, which is what we call the closed loop transfer function. Now, closed loop transfer function is actually the same as plant without feedback. Now, if you, I don't know at this point of time, have you read until, or have you watched until all the videos or lecture notes that that cross the block diagram manipulation for Rule 7 or Rule 8? Now, Rule 7 and Rule 8 says that if you have a transfer function, forward transfer function, and a reverse transfer function, for this case, the feedback transfer function is 1, then you would use G over 1 plus GH if it's a negative feedback, or if you will use G over 1 minus GH if it is a positive feedback. Now, for this case, it is a negative feedback. So this transfer function is gotten by using this G here on top here, and the H will be 1. So it's G over 1 plus GH, and then you simplify it, you will get this transfer function. So with this new transfer function, you key it in and you run, you will realize that both of them, the shape is the same. One of them is physically connecting in the negative feedback fashion. The other one is basically the mathematical equivalent. That means after you calculate and simplify, you just key in the numerator and denominator, you should get exactly the same for plant with feedback or the closed loop transfer function. It should be exactly the same, right? Now, in the details, of course, when I give you the template, I will deliberately miss out all these things. Of course, cannot be everything for free. So deliberately, all this line will not be drawn in. So what you need to do is to just connect up the line. Please don't delete the symbol, because if you delete the symbol, then you have to have a very hard time referring to the reference menu to find how to insert each of the symbol, right? So basically that's it. So for plant only is basically talking about this graph, and plant with feedback is talking about this graph, and of course closed loop transfer function is talking about this graph, right? Basically all are given for you. You just need to wire up and then do the simulation of the running. So exercise 1 and 2, basically we are using one first order transfer function, which is 2 over s plus 0.1, right? 2 over s plus 0.1. So of course the plant only will be a direct input, a step function. You check the output, right? Of course, for exercise 2, it will be instead of just direct input and straight to the output, there is a feedback of 1 unity feedback, and of course it's a minus negative feedback. So that is exercise 1 and 2 configuration. Now, of course, when you talk about the third one, the third graph, we will be using the block diagram manipulation rule. This is rule 7, which is G over 1 plus GH. This is the block diagram simplification rule 7 that we have been using in beginning of chapter 4. And of course, if you use this, then you would be able to solve the equivalent for closed loop transfer function for this guy. And then with that, you can plug in into the last graph, right? Okay, so that is for the first order. Now, as for the second order, it's slightly different because second order is, of course, more complex. But of course, this course, we don't go to third order, fourth order, because it will get too complicated. So we basically stop only at the second order, second derivative and the first derivative, and of course the non-derivative plus by the constant function, right? So if you take the Laplace transform, rearrange it, you will get probably be able to get something close to a generic transfer function of k omega n squared over s squared plus 2 zeta, zeta which is the damping ratio, omega n s plus omega n squared. Now, this is called the second order transfer function because, again, like I say, the denominator is the most important function of any control transfer function, right? So we look at the denominator function and look at the highest power. So with the highest power of 2, we conclude that this is a second order transfer function, right? So omega n is your undamped natural frequency, which occurs when zeta equals to 0, right? That means there is no damping. And then, of course, damping, zeta is the damping ratio, and k is the steady state value, or rather a steady state gain. So these are the three terms that make up of the entire second order transfer function. You can see k, omega n, zeta, omega n. So everything is just make up of this three term, right? If you vary this three term, your transfer function change quite drastically. Now, when we say k, omega n is the undamped natural frequency, it occurs when damping ratio is equals to 0. It means that when damping ratio equals to 0, now you can view damping ratio as a break to the oscillation, right? It's like a resistant to oscillation. When you have damping ratio to the equals to 0, it means that the resistance to oscillation is basically 0. So there's no resistance to oscillation. So basically, the whole transfer function, which is a negative feedback, will start to oscillate like crazy, right? So it's a entirely oscillating function. So that's how it looks like when your damping ratio. You see the sliding scale. I slide the damping ratio to 0, and then of course the natural frequency will damp at 2.5, right? Right. So that's basically how it looks, right? Now, if you change your damping ratio, of course, slowly, if I increase it, it will start to go into this range, which is between 0 and 1. This is what we call an underdamped case, right? Underdamped situation. Underdamped situation means that we apply a little bit of brake, but not so much. So you can see that the oscillation start, but it was damped away until it settles to the final steady state value K. So this is what we call an underdamped case. And in fact, this case is most studied after, because there's a lot of usefulness of this case, right? Now, if you start to increase the damping ratio further until it hit a value of 1, this is what we call the critically damped, right? Critically damped, whereby the transfer function will just grow up like the first order system, and then it settles down at the steady state value K, right? Now, if you increase further, of course, you will also behave the same way, but this time around it's even slower, and it will just gradually go up to K. Now, take note that for the case of underdamped, critically damped, and overdamped, all three of the situation, it will settle down at a value of K, right? Whereas for the underdamped, there is no steady states. It is always up and down, up and down, up and down. Oh, so that is the difference between all this, right? Now, if you look at the in terms of the solution at the denominator. So basically, if you look at the second order transfer function, this is a second order function. If we try to solve, this is a second order, right? Squared. So squared term will result in 2 roots, right? So these 2 roots is the one that we are talking about here. So if you look at the case for underdamped, right? Underdamped will result in the 2 roots being in this form. Don't ask me why. You try to solve it, you should be able to get it, right? So so basically you would have a basically complex root, because there is a J term here. 2 complex conjugate roots. So that is for underdamped. Now, for the case of critically damped, you would have 2 negative identical roots. So it means S1 and S2. Sorry, the roots for the denominator will basically be minus omega n. Now, if you have an overdamped case, then you have 2 real negative roots. 2 real negative roots. Notice that there is no J here. So without J, you have 2 real negative roots. They are just numbers, right? Okay. So now I'm going to show you the damping ratio, one of the VI that has been created for demonstration of damping ratio. Without further ado, let me go and turn on the transfer function, and I stop sharing here. Basically, let me stop sharing here, and let me go to the file. For damping ratio, right? Now let me share the damping ratio file. Where did I have it? Okay, I have it here. Now, if you look at the damping ratio file, let me hide the control panel so that you can see the whole thing in totality. Now, this damping ratio file basically looks this way, and I'm not sure if I can. Give me a while. Okay, so basically for this damping ratio file, you can change the scale for damping ratio from undamped, which is 0, to underdamped. Of course, you can change it to overdamped by changing the scale. If I right click, change the property, then I can change the scale to say instead of 1, I can change it to 10, right? And then you can continue sliding. Right? You can continue sliding the damping ratio from this all the way to overdamped. Right, of course, the undamped natural frequency, we can just predetermine a value. Let's say I set it to 2.5. Now, if I do a continuous run, if I do a continuous run, this stipulate an overdamped case. Let me begin the whole thing by going into the undamped case. Now for the undamped case, when damping ratio is equal to 0, you realize that the output actually oscillates, right? Oscillates, right? Of course, if I stop the function, then it will plot the waveform chart over at this bottom here. But now I'm not going to stop it because I just need you to focus on this part here. And you realize that because this is a second order transfer function, this is something like omega n squared over here, over this is omega n squared as well. This is s plus 2 zeta omega n, but the zeta is 0, therefore the center terms is 2 zeta omega n s, right? Is 0 because the term is, remember the generic equation that I showed you just now? This is 2 zeta omega n s. So basically this is the makeup of the whole transfer function. Now if I move this slightly to about the underdamped case, whereby it is between 0 and 1, now you realize that the damping start to occur, but it cannot sustain and it is being damped away. So there is still reasonable amount of breaking that we break away the oscillation. And by doing so, you can see that the omega n squared and omega n squared here, and this is s squared, and this is 2 zeta omega n. So this zeta come into play, right? Now this zeta is no longer 0. So therefore zeta come into play. And then, of course, if you try to increase it to, say, a zeta of 1, about 1, so you can see that my zeta is about 1 now. So again, the slope will be slower, and then you don't have a peak and throw there, right? So again, the same goes for the numerator and denominator, right? And of course, you can also further do it for overdamp all the way up to a very high value of 10. Of course, this will get slower and slower, but because we have an auto scale, you don't really know it, that the scale is changing, and you don't really see the effect of slowing down, right? But it's okay, we know it, right? So basically, if I change the omega n, you realize that 3 term is changing for this transfer function, which is a numerator, and as well as the s term and s to the power of 0 term. So you can see that these 2 terms are changing, whereas the s squared don't change, of course, right? So it affects the 3 term, right? Now, of course, if I change the damping ratio, it only affects the 1 term, which is the middle term here, which is consistent with the second order transfer function that we have shown earlier, right? So with that, I will go back to the PowerPoint presentation. So just now we just mentioned about the second order transfer function, which is zeta only affects the denominator second term, whereas omega n affect the 3 terms, one on the numerator, the other one for the s term and the s to the power of 0 term, right? So that's a demonstration for damping ratio. Now we proceed on to section 2, which is what you are supposed to submit for the submission for Lab5. Of course, the section 2, we already told you it is a second order transfer function because the denominator is s squared. And then this is, of course, because the highest power is s squared, therefore it's a second order transfer function. So for exercise 3 is basically for the plant only, and exercise 4 will be for the plant with feedback, right? And then, of course, there will be another one, closed loop transfer function, whereby you need to calculate the G over 1 plus GH. And of course, exercise 5 and 6 also, it will be the same thing. But now for exercise 5 and 6, we are using 1 over s plus 2. Now, if you multiply this out, the highest power will be still s squared, right? So that's why we also call it the second order transfer function. Now, later I'm going to demonstrate to you the solution for exercise 5 and 6 so that with this solution, you'll be able to infer how to do it for exercise 3 and 4, right? Now, the calculation for T-rise, of course, in the question, there will be asking you to calculate T-rise, settling time, peak overshoot. Basically, we use the formula sheet. After finding omega n and zeta. Sorry, I didn't change the sign for this zeta. It should be the other transfer, something like a snake. So basically, this is the O symbol that is being used. So the hint is to compare the denominator, right? Compare the denominator of your closed loop transfer function with the generic equation. That means the denominator of the generic equation, which is s squared plus 2 zeta omega ns plus omega n squared. And then closed loop transfer function will be your closed loop transfer function that you calculated from G over 1 plus GH, right? So by comparing the two denominator, you'll be able to calculate, we'll be able to find omega n and the damping ratio. Now with omega n and damping ratio, you go to the formula sheet, you will be able to solve for T rise, T settling, T peak. In fact, omega and zeta will be the one that is the key to find all the timing parameters. So for the calculation of the steady states, there's also other parts whereby you need to calculate the steady states. We will use the final value theorem, whereby error of steady states is actually given by limits. If you take the limits of s approach 0 when you multiply a small s with your original transfer function. Now, say basically you will also use u of s is equals to a step function, unit step function. So basically, if usually it's this way, and if you try to solve it, you'll realize that most of the time for steady states error, E of s divided by the input transfer function, you will get 1 over 1 plus g of s h of s. So the closed loop transfer function calculation is g over 1 plus gh. So can you contrast the difference? The only difference is the numerator that is different. For error, it is 1 over 1 plus gh. For closed loop transfer function is g over 1 plus gh. So basically, that's the different thing, right? So let me now show you how to one of the example in the that we use. Give me a while. Okay, now there is an example that I have attached inside, which is for exercise 5. So now I'm going to share with you the example for exercise 5. Now, how come I don't see it? It's in the Words document. Where's my Words document? It's here. Okay, so basically you can see here, this is an example for 5 and 6, exercise 5 and 6. If you can recall, the expression is 1 over s plus 2, right? So if you multiply the s in, you will get s squared plus 2s. Now the first question is asking you determine the order and the type. So how do you know the order? As we have already mentioned, the order is always looking at the denominator and check the highest power. Now, for this case, the highest power is 2, so therefore the order is second order, right? Now, how about the type? Type, we have to look at the s plus, this s is equivalent to s plus 0. It's just like s plus, bracket s plus 0 times by bracket s plus 2, right? So this is equivalent to this. So this is, when you have s plus 0, it means the roots is at origin, right? So if these roots at origin, if the power is 1, so s means s to the power 1. So therefore, if it is s to the power 1, then it is type 1. So we have already answered this order and type for this case. Now for exercise 3 and 4, you got to go and figure out what is the order and type for this case, right? Now the second part of the transfer function, the exercise for exercise 5, they say enter the transfer function for the plant only of Lab5-2. So remember, just now we mentioned there is plant only, and basically is referring to this portion here. You just need to key in this portion here for plant only. Okay. Now I go back to this case. I share again. This is a plant only. So you look at it, for numerator, I have s to the power of 0 as 1, right? So 1 here, I put in a 1 here. Right? Now for denominator, I have s squared. So I put 1 times s squared is s squared, right? Now I have 2s. So it's 2 times s is 2s. I don't have s to the power of 0, so I put 0. So that this is basically to describe your plant transfer function. Now, once you key in this already, you need to set your chart. Go to your front chart here. Basically, go to your front panel. Okay, you go to your front panel here. You right-click on the chart here. Right-click on the chart here. Okay, right-click on the chart here. And then select the chart history length to 1024. Now, this is basically to extend the simulation up to about 10 seconds for this case. So whatever they try to tell you to do, you just follow. Now, so they say edit the control simulation loop parameter, which is at the back to 10. So you just follow the lab sheet, go and adjust the final time to 10 seconds. Then you create the run, right? Run BI. So you realize that the open loop, the plant only, or rather the open loop, this is plant without feedback. The system, when you do a step function of 0 to 1 volt, it actually runs all the way up to 5 volt. So this is the characteristic. Now, then part F, it asks you from your observation, of the output, is it a self-regulating or an integrating system? So which one? So of course, for this case, I look at it, it is an integrating system. Why? Because when the output already stopped, when the input already stopped at 1 volt, the output continues to rise. So regardless of the input. So therefore, this is an integrating function. For a self-regulating function, if the output input already stopped, then they will basically also stop at certain level. They will settle down. Now, comment on the output response with respect to the input apply in terms of speed and accuracy. So they ask you to comment in terms of accuracy and speed. Okay, for speed wise, the output rises very slowly. When 1 volt is applied, 1 volt steps is applied. So you can see when I put a step function here, it takes very long time to reach 1 volt. And of course, after that, it cross 1 volt. So our intention is to look at how long does it take to reach 1 volt. So it takes quite a few seconds. You look at this scale here of 10, this 10 division, it takes about 2.5 seconds to reach 1 volt. So we'll consider that slow. Now, accuracy-wise, is not accurate, right? So because we want it to settle at 1 volt, but it go all the way up to 4.7 volt in 10 seconds. So you can see it go up all the way to 4.7 volt in 10 seconds. So it's actually not accurate, and there's an error here. The desired output is actually 1 volt, but it go all the way up to 4.7 volt. So there's an error of around 4.7 minus by 1. So it's about 3.7 volt. Right. So now we try to configure the second one, which is the plant with feedback. So of course, plant with feedback, and then so basically for plant with feedback, you can go back to the transfer function again. Now here you key in the controller as 1/1, right? 1/1, 1 here. Then the other 4 column you put it as 0 0 and you run. So this will be your plant with feedback, right? Plant with feedback. Right? So after the configure, then they ask you to calculate what is the for negative feedback, right? So basically you can do a calculation for closed loop transfer function. That is for the third part. So closed loop transfer function is G over 1 plus GH. This is G again, which is your forward gain, and then H is a unity feedback. So by doing this calculation, you can realize that 1 can be converted into S plus 2 over S plus 2, right? So this is again still 1. I never change anything. So with the same denominator, I can add them, right? So right now, because both of them, the top and the bottom is having the same denominator, the denominator can be cancelled away. So what is left is the numerator on top and the numerator at the bottom, which is S plus 2 plus 1. So what happens is if you multiply and expand it out, it will become 1 over S squared plus 2S plus 1. So this is your closed loop transfer function that you simplify and find out to be. Now, of course, for the damping ratio, if you were to calculate it theoretically, so in theory, this is your closed loop transfer function, and this is the denominator, right? Denominator of the closed loop transfer function. So the denominator for closed loop transfer function is repeated here, right? Now, how about the generic transfer function? Generic transfer function, remember just now we mentioned generic transfer function is basically for second order. Let's see, where's your second order? Let me scroll to the page. This is your second order. The generic equation is this denominator here. Okay, this denominator here. So which is exactly what has been shown here, right? So generic equation here. So of course, for the both of the expression to be exactly the same, that means the s squared term is equal to the s squared term. That's agreeable because it's just s squared. Now the 2s must be equals to the 2 zeta omega ns. So if we look at it, 2 zeta omega ns must equals to 2s. Now with that, you can solve zeta is equals to 1 over omega n, which is 1, right? Then of course the n term, the last term, 1 must be equals to omega n squared, right? So omega n squared is equal to 1, then omega n must be equals to 1. So if you substitute 1 here, then zeta also is equal to 1. So which means that it's trying to tell us that since zeta is equals to 1, that means the system is under a critically damped situation. It's not an under damped situation, it's a critically damped situation. So the rise time, of course, you can use your omega zeta and omega n that is calculated already, plug it into your into the finding from the formula sheet. We find the rise time for 0% to 100% is pi minus beta over omega d. Now pi, of course, remain as pi, which is 3.142. Beta is cos inverse of damping ratio. Now cos inverse of 1 is actually 0, right? Cos inverse of 1 radian is 0. Now again, denominator is omega d. Omega d is omega n multiplied by 1 minus squared of zeta. So 1 minus by 1 squared is actually 0, right? Again, 0 at the bottom. So 0 divided by 0 is actually infinity. So the time is really very huge, right? So it's not defined. Now settling time, again, is using the formula sheet. You look at settling time, and it's 4 over zeta omega n, right? So 4 divided by zeta, zeta again calculated as 1, right? Zeta calculated as 1, damping ratio as 1, and omega n also calculated as 1 here, right? So basically you plug it in, you get 4 seconds. Now, will there be a picking? Will there be an overshoot? Because it's a critically damped, we don't expect any overshoot, right? So the steady state error for this case will be 1 over 1 plus GH. Remember, we say that it's not G over 1 plus GH, but rather 1 over 1 plus GH. Now again, you plug in your G here, and you recalculate and simplify your E over U of S will be having this transfer function. Now again, U of S, we are using 1 over S, right? So if we take the limit of S multiplied by E of S, which is S multiplied by E of S is actually this transfer function multiplied by U of S. So this is E of S over U of S, this one, this term here, right? E of S over U of S, and this is U of S. So E of S over U of S multiplied by U of S, you cancel out, this is actually E of S. The whole thing is E of S, right? So basically E of S, which is actually this term here. Now if you multiply them, and then you let your, of course, this S here, 1 over S here, will cancel with your S term. Also, you S cancel with S, so basically you are left with your this term here, which is E of S over U of S, or you are left with this term. Now, if we put the S tends to 0, which means that eventually your S will become 0 for all the S here. So S times 0 times anything will be 0 on top. 0 times anything plus by 1 will be 1 below. So finally, your steady state error will be 0 volt for the case of E. Right? So this is quite straightforward for the computation of part 3. Now, with plant with feedback, of course, we also can run the simulation, which is just now the case where I told you to set the controller is 1, 1 and the other 4, 0. When you run it, you basically, if you right click at here and you set to digital display, you would have 2 reading. On top is your input, which settle down at 1 volt. And the second bottom here is the output here, which also settle down at 1 volt. So your steady state error is actually the difference between the desired output and the actual output. So basically 1 minus by 1, you get 0 volt, which is very consistent with what we have just calculated as 0 volt. Right? We calculated as 0 volt. Now, the rise time and the settling time is we roughly calculate whereby it's more or less flat. So this is about 7 seconds. So settling time is about 7 seconds. Now from from 0 to 90%, maybe it's about 6 seconds for the system to rise from 0 to, we calculate for what, 0 to 100%. So this is about 0 to 100% is about 6 seconds, right? So from the graph, determine the rise time. Rise time is about 6 seconds, as we have read here, right? From 0 to 100%, about 100% is about 6 seconds. Of course, reading is always about. Then determine the settling time of the system. Settling time of the system is about 7 seconds. And is there any peak overshoot? There is no peak overshoot. As you can see, there is no overshoot. Nothing goes beyond 1, so there is no overshoot, right? And then from the graph, ESS is equals to 0. Why? Because we see that the final value and the intended value, both of them are at 1 volt, so there is 0. And then if we calculate the damping ratio from this case, omega n squared equals to 1, then omega is equals to 1. Then settling time will be 4 over zeta omega n. Again, your zeta with a settling time of 7 will be 0.571. So this is a reverse calculation of zeta, right? Now, verify the result obtained in step 3 with that of step 2, right? So step 3, step 2, clearly the system is critically damped for both cases. They are having critically damped based on step 2 calculation, and hence there is no peaking. This is consistent with the step 3 result. Both of them are pointing to it as critically damped. But the rise time and settling calculation in step 2 calculated. Step 2 is the calculated one. Step 3 is the simulated one. So from there, we obtain for the calculated, the rise time is actually infinity, but the actual simulated is only 6 seconds. So there is some deviation. Maybe it's because the formula is used for under damped, but right now we are using it for the critically damped situation. So therefore, the formula is not really accurate, right? And then of course, the calculated settling time is about 4 seconds, whereas the simulated settling time is about 7 seconds. Okay, that's not as far as the rise time calculation. So yeah. So as for the rise time and settling time using the formula for under damped, because all the formula in the formula sheet for rise time, peak, everything is for under damped case. That means 0 between the zeta between 0 and 1 situation. So we are using it to calculate for critically damped, whereby zeta is equal to 1. So hence we can say that settling time and rise time in step 2 is not really accurate, because the calculated one is not really the correct formula to use. Then the last part, they ask you to derive the closed loop transfer function with plant with feedback, right? So this one we already did it before in the earlier part here. We did it before already, right? So we did it here at the beginning here. Now we just copy that and put it below here. Copy that and put it below here. And then of course, with this, we just need to key in the closed loop transfer function in the bottom left-hand corner, which is over here. Let me see. Okay, which is over here. This is a closed loop transfer function. You just need to key in the numerator and denominator here, right? Numerator with denominator over there. So basically, you put your numerator as 1. Denominator, it will be s squared is 1, right? S squared. Then s is 2, right? 2 times s. So 2s. And 2 times s to the power of 0. This is s to the power of 0, not a0. So s to the power of 0. So 1 times s to the power of 0 is 1. S to the power of 0 is 1 anyway. So therefore, this is your closed loop transfer function input. So by keying in this input and you do a run, you would actually get the same curve, right? You get the same curve. For this is for your with feedback curve. You realize that the with feedback curve looks this way, and also for your closed loop transfer function curve also look the same. So observation is that both the simulated for plant with feedback is the same as the closed loop transfer function. This is because of rule 7 of block diagram manipulation. That means the rule 7 of block diagram manipulation is actually very accurate, right? So because of this, the mathematical calculated expression and the actual feedback give you exactly the same result. So this is basically exercise 5 and exercise 6. So with that, I pretty much finished the presentation for Lab 5 theory as well as the requirement for the submission. Just a reminder again, you need to submit it by the end of week 8, which is the date is given in the submission folder there. please, you can discuss, but please do not submit exactly the same. Again, if I check that there is a similarity of more than 80%, marks will be deducted. Beyond the time, I will not be giving any personal favor. As in, Chair, can you give me longer time? There's no such thing. If you cross by 1 day, 10% deducted. 2 days, 20% deducted. Third day, you deduct to drop to 70%. And so on and so forth. You get drop more and more. So until you get 0. So basically, that's it. I wish you all the best and thank you.